Hi everyone, welcome back to my Icnarium Chemistry YouTube channel. In this video, we will discuss about coordination compounds. Let us know about what is the difference between covalent bond and coordinate covalent bond. First, we will consider atom A, which has 1 electron, and atom B, which has 1 electron. So here, in order to form bond between A and B, we know that 2 electrons are required. So here what happens is, both A and B donate 1 electron each to form bond between A and B. Okay, that means here mutual and equal sharing of electron is taking place. Equal sharing of electron is taking place. Okay, so this type of bond is called as covalent bond. Covalent bond. We will consider another case, that is A has 2 electrons and B has no extra electrons. Okay, so in this case, both the electrons of A are being donated to B in order to form bond between A and B. Here, unequal sharing of electron is taking place. Unequal sharing of electron is taking place. This type of bond is called as coordinate covalent bond or coordinate bond. Coordinate bond. Okay. So in covalent bond, mutual and equal sharing of electron is taking place, but in coordinate bond, unequal sharing of electron is taking place. Only one of the atom donates the electron in order to form bond, which is nothing but coordinate bond. We know that metals have tendency to lose 1 or 2 electrons to form positive ions. Okay, therefore, if you consider lithium, okay, which donate 1 electron and becomes lithium plus. Okay, if you consider magnesium, it donates 2 electrons and becomes Mg2 plus. Okay, likewise, if you consider Mn2 plus, Fe2 plus, Cu2 plus. Okay, so metals are electropositive in nature. This indicates metals have tendency to lose electrons, okay, and becomes positive ions. Therefore, metals are electron deficient. Since the metals are electron deficient, they accept pair of electron. Therefore, they are called as electron pair acceptor. Electron pair acceptor. Since the metals are electron deficient and electron pair acceptor, it acts as electrophile. And we know that electron pair acceptor is a Lewis acid. Lewis acid. So, metals are electron deficient. Okay, since they are electron deficient, they accept pair of electrons. Therefore, they act as electron pair acceptor. Okay, since they accept pair of electrons, they also act as electrophile and which also act as Lewis acid. Okay, let us know about what is ligand. We will take an example, that is NH3. Okay, we know that nitrogen has a lone pair of electron and this lone pair of electron is being donated to the metal atom. Okay, in the ligand NH3, okay, nitrogen has the lone pair of electron and this lone pair of electron is being donated to metal M. Therefore, NH3 is a ligand. We will define what is ligand. So, ligands are ions or molecules. Ions are molecules which donate at least one lone pair of electron to the central metal atom to form coordinate bond. Okay, the ligands are ions or molecules which donate at least one lone pair of electrons to the central metal atom to form coordinate bond. For example, NH3. We will take one more example, that is H2O. Here oxygen has a lone pair of electrons. Okay, and here this lone pair of electrons are being donated to metal, therefore H2O is a ligand. We will consider Cl minus. Okay, here this negative charge indicates the presence of 2 electrons, therefore these electrons are being donated to metal, hence Cl is a ligand. Coming to Cn minus, again here this negative charge indicates the presence of 2 electrons, therefore these electrons are being donated to metal, hence Cn minus is also considered as ligand. And you can notice that here NH3 has lone pair of electrons, H2O has lone pair of electrons, Cl has negative charge and Cn also has negative charge. That means ligands are electron rich species. Electron rich species. Okay. Since they are electron rich, they donate electrons, therefore they are electron donors. Electron donors. Since they donate electrons, they also act as nucleophiles. Nucleophiles. Since they donate electrons, they also act as Lewis base. Lewis base. Okay, these are all the properties of ligands. Consider metal, okay, to which group of ligands are attached. To which group of ligands are attached. We know that ligands are electron rich species, hence they donate electrons to the central metal atom, okay, to form coordinate covalent bond. This is called as coordination compound. Here the group of ligands are attached to the central metal atom through coordinate bond, therefore this is nothing but coordination compound. Now we will define what is coordination compound. The compound in which a metal is attached to a group of ligands through coordinate bond is called as coordination compound. Okay, we will take an example, that is CONH3 3 times and Cl3. This is an example for coordination compound. Here cobalt metal is attached to 3 NH3 ligands and 3 Cl ligands. 3 NH3 ligands, here NH3 and here NH3, here Cl, Cl and Cl. Okay, this is called as coordination compound. This is called as coordination compound, which are also called as complex compound. Okay, coordination compounds are also called as complex compound. Now we will see what is complex ion. What is complex ion? Okay, here the complex ion is the charged species. It is a charged species containing a central metal ion, attached to group of ligands through coordinate bond. Okay, this is nothing but complex ion. We will take an example. CuNH3 4 times, okay, which has charge 2 plus. Okay, here this is the coordination compound, or which is also called as complex compound, which has charge on it. Okay, the charge is 2 plus. Okay, therefore this is called as complex ion. We will take one more example, that is FeCN6. The charge is 4 minus. Okay, this is the coordination compound or complex compound which has charge 4 minus. The complex ions are the charged species which contains the central metal atom which is attached to a group of ligands through coordinate bond. This is nothing but complex ion. This coordination compounds are classified into three types. Okay, first one is cationic complex. Okay, so these are the complex which ionizes. In the solution to give positive complex ion. Okay, for example, we will take CuNH3 4 times SO4. Okay, this is cuproammonium sulfate which ionizes in the solution to give CuNH3 4 2 plus SO4 2 minus. Okay, so here this is the complex which has positive charge, therefore it is a cationic complex. And next type is anionic complex. So these are the complex which ionizes in the solution to give negative complex ion. Okay, for example, K4 FeCN6. Okay, this is the coordination compound which ionizes to give 4K plus FeCN6 4 minus. This is the complex compound which has negative charge on it, therefore it is anionic complex. And the third type is neutral complex. So these are the complex which does not ionize in the solution, Okay, therefore these neutral complex will be having no charge on it. We will take an example. Nickel tetracarbonyl is a coordination compound or complex compound which do not ionize in the solution, therefore it will be not having any charge on it, therefore it is a neutral complex. Next example is COCl3, okay, NH3 3 times. Okay, this is also an example for neutral complex because this do not ionize in the solution. Next we will go for types of ligands. Okay, ligands are classified based on the number of donor atoms present in the ligand. First we will know what is donor atom. Okay, consider ligand NH3. Okay, this is ligand. Here nitrogen has lone pair of electrons and this lone pair of electrons are being donated to the metal atom. In the ligand NH3, only the nitrogen is donating the lone pair to the central metal atom. Therefore, nitrogen is donor atom. So, donor atom means atom in the ligand. Okay, atom in the ligand which donates lone pair of electron, to the metal atom. Next we will see about what is denticity. Okay, here the denticity means number of donor atoms in the ligand bind to the central metal atom. bind to the central metal atom. Okay, denticity means number of donor atoms in the ligand, okay, which bind to the central metal atom. Again we will consider NH3 ligand. Okay, NH3 ligand. Here nitrogen has lone pair of electrons, and this lone pair of electrons are being donated to metal. Therefore nitrogen is the donor atom. Here only the nitrogen is binded to the metal atom. Therefore denticity of NH3 is 1. We will take few more examples. Consider again NH3. Nitrogen has lone pair of electrons which donated to the metal atom. How many donor atoms are there here? Only nitrogen is the donor atom. Therefore, one donor atom. What is the denticity here? Here only the nitrogen is binded to the metal atom. Therefore, the denticity is 1. We will take one more example, that is oxalate ion, COO minus and COO minus. So, how many donor atoms are there here? This is one donor atom and this is another donor atom. Therefore, two donor atoms are there. What is the denticity of this ligand? 2, because your two donor atoms are attached to the metal atom. Therefore, denticity is 2. We will take one more example, that is NH2, CH2, CH2 and here NH2. Okay. How many donor atoms are there in this ligand? Here nitrogen has lone pair of electrons and here also nitrogen has lone pair of electrons. Therefore, two donor atoms are there. Okay. And what is the denticity of this particular ligand? These two donor atoms donate a lone pair to the metal atom. Therefore, denticity is 2. This is how you have to identify donor atom and also the denticity. Now we will look into the classification of ligands based on donor atoms. The first classification is monodentate ligands. Monodentate ligands. These are the ligands which contains one donor atom. One donor atom. We will take some examples. We will take NH3 again. We know that nitrogen has a lone pair of electron and this nitrogen donates lone pair of electron to the metal atom. Okay, therefore it has only one donor atom, right? Yes. This is an example for monodentate ligand. And we will take H2O. Here oxygen has lone pair of electrons. Okay, out of these two lone pair of electrons, one lone pair of electron is donated to the metal. Therefore, only one donor atom is there. It is an example for monodentate ligand. We will take Cl minus. Okay, this is also monodentate ligand, Cl minus and etc. And the second type is didentate ligand. Didentate ligand or ligands. Okay. So these are the ligands which contains two donor atoms. Ligands which contains two donor atoms. Consider COO minus. Here COO minus. How many donor atoms are there in this ligand? This is one donor atom and here this is second donor atom. Therefore, two donor atoms are present. Therefore, it is an example for didentate ligand. We will take one more example, that is ethane 1,2-diamine. If you write the structure of ethane 1,2-diamine, here NH2, CH2, NH2. This is the structure of ethane 1,2-diamine. Here nitrogen has lone pair of electrons. Yes, both the nitrogen has lone pair of electrons and these lone pair of electrons are being donated to the metal atom. Therefore, it has two donor atoms, which is an example for didentate ligand. Here, this ethane 1,2-diamine can also be written as En. Okay. Tridentate ligand. These are the ligands which has, which contains three donor atoms. 3 donor atoms. For example, diethylene triamine, diethylene triamine, triamine, which can also be written as diene. Okay, diene. If you write the structure here, NH2, CH2, CH2, here NH, here CH2, CH2, and here NH2. How many donor atoms are there here? 3 donor atoms. Okay, here nitrogen has lone pair of electrons, and here nitrogen has lone pair of electrons, and here also nitrogen has lone pair of electrons. Therefore, these 3 nitrogens will donate a pair of electron each to the central metal atom. Therefore, it is an example for tridentate ligand. Next, we will go for polydentate ligand. Polydentate ligand. These are the ligands which contains two or more than two donor atoms. Two or more than two donor atoms. Okay. We will take examples, that is triethylene tetraamine. Okay. If you write the structure, that is NH2 single bond CH2 CH2, and then NH, again CH2 CH2, NH, again CH2 CH2, NH2. How many donor atoms are there here? 4 donor atoms. Okay, here nitrogen has lone pair of electrons, here also lone pair of electrons, here lone pair of electron, and here lone pair of electron. Therefore, all the 4 nitrogen atoms will donate lone pair to the metal atom. Here 4 donor atoms are there, which is also example for tetradentate ligand. Tetradentate ligand. We will take one more example, that is EDTA4 minus. EDTA4 minus. Here EDTA means ethylene diamine, tetraacetato. Okay, this is the name of the ligand. If you write the structure of EDTA4 minus, okay, here nitrogen, CH2, nitrogen, and here CH2COO minus, and here CH2COO minus, here CH2COO minus, here also CH2COO minus. How many donor atoms are there here? Here negative charge, here negative charge, here negative charge, here negative charge. Therefore, 4 donor atoms. Along with that, there are 2 nitrogen atoms are there. Here nitrogen atom has lone pair of electron, here also nitrogen has lone pair of electrons. Here 4 plus 2. Therefore, 6 donor atoms are there. 6 donor atoms are there. It is an example for hexadentate ligand. Hexadentate ligand. EDTA4 minus is an example for polydentate ligand. In specifically, it is example for hexadentate ligand. Okay. Next, we will move on to chelate ligand. Chelate ligand. Okay. These are non-cyclic di or polydentate ligands. Which donate two or more pair of electrons simultaneously to the central metal atom to form ring-like structure. We will take example, that is ethylene diamine. Okay, En means ethylene diamine. Ethylene diamine. Okay, consider a metal ion to which 3 ethylene diamines are attached. 3 ethylene diamines are attached. Okay, we will write the structure here. Here nitrogen CH2, CH2 and nitrogen. Here nitrogen, here also nitrogen, CH2, CH2, nitrogen. Nitrogen, nitrogen. Here nitrogens are donating the lone pair of electrons simultaneously to the central metal atom, and which is also forming ring-like structure. Ring-like structure. Okay. Therefore, these type of ligands are called as chelate ligands. Okay, and these type of complexes are called as chelating complex. Chelating complex. And here one more example is ethylene diamine tetraacetate 4 minus. This is also chelating ligand. Next we will move on to ambidentate ligand. Ambidentate ligand. Ambidentate ligand. These are monodentate ligands. These are monodentate ligands which are having two different donor atoms. Having two different donor atoms. Two different donor atoms. But only one donor atom. Only one donor atom is coordinated to the central metal atom. Okay, central metal atom. We will take an example, that is SCN. Okay, this is the ligand. So in this ligand, if you write the structure S double bond C double bond N. Okay, S double bond C double bond N. Here nitrogen will be having negative charge. Okay, sulfur will be having lone pair of electrons. So that sulfur will also act as donor atom and nitrogen will also act as donor atom. But only one of these donor atoms will coordinate to the central metal atom. Okay, hard metal coordinated to nitrogen and soft metal coordinated to sulfur. Soft metal coordinated to sulfur. Here hard metal means metals which has high charge, small size, higher electropositivity. Okay, higher electropositivity. And coming to soft metals, okay, these are larger in size, and which has lower electronegativity. That is Ag plus is coordinated to sulfur, N triple bond, C single bond, yes. Okay, here sulfur is coordinated to Ag plus and nitrogen is coordinated to cobalt 3 plus, that is S double bond C double bond N. Okay, here nitrogen is coordinated to cobalt 3 plus. Okay, we will take another example, that is SO3 2 minus. If you write the structure of SO3 2 minus, that is S double bond O, here double bond O and here also double bond O. So here oxygen has a lone pair of electrons, here oxygen has lone pair of electrons, here also oxygen has lone pair of electrons. The condition to be ambidentate ligand is it should contain two different donor atoms, but here only one type of donor atom is there, that is oxygen. Therefore, this is not ambidentate ligand. If you write the structure of SO3 2 minus in this way, okay, that is S double bond O and here S single bond O minus and here S single bond O minus. So in this case, sulfur will be having lone pair of electrons. Therefore, sulfur also acts as donor atom and oxygen also acts as donor atom. But out of these two donor atoms, only one donor atoms coordinate with the metal. Therefore, this is an example for ambidentate ligand. Next, we will go to bridging ligand. Bridging ligand. The ligand which connects two or more metal atoms or ions. Metal atoms or ions. Okay. So here the bridging ligand can be denoted by the symbol mu. Okay. Wherever you see the symbol mu, you have to think of the bridging ligand. Here this ligand should have at least 2 lone pair of electrons. Okay. Ligand should have at least 2 lone pair of electrons. Okay. Let us take the example Cl minus. If you write the dot structure of Cl minus, okay, 2 electrons, here 2 electrons, here 2 electrons, and here 2, because Cl has minus charge. Okay, here these 2 lone pair of electrons is being donated to the metal, and here also these 2 lone pair of electrons are being donated to the metal. Okay, therefore here this Cl which is connecting two metals, therefore which is acting as a bridge, hence it is an example for bridging ligand. If you take the proper example, here Cl, okay, coordinated to CrH2O, CrH2O 5 times, okay, and here CONH3, CONH3 5 times. Okay, this is the coordination compound in which Cl is a bridging ligand. Okay, we will take one more example, that is N double bond, C double bond. Yes, we know that sulfur has 2 lone pair of electrons. Okay, this lone pair of electron is donated to metal. Here also this lone pair of electron is donated to metal. This is an example for bridging ligand. If you consider NH3, okay, here nitrogen has only 1 lone pair of electrons, so that it is not a bridging ligand. But if you consider H2O, oxygen has 2 lone pair of electrons, therefore which can act as a bridging ligand. This is a bridging ligand. The bridging ligands act as bridge, okay, act as bridge between two metal atoms. Next we will go on to flexidentate ligands. Flexidentate ligands. Okay, these are polydentate ligands. These are polydentate ligands. Okay, which shows variable denticity, according to the requirement of the metal. Okay, flexidentate ligands or polydentate ligands which shows variable denticity according to the requirement of the metal. CONH3 5 times SO4. Okay, this is the coordination compound which has positive charge. If you write the structure of this coordination compound, that is CO is coordinated to 6 ligands, right? That is 5 NH3 ligands, here NH3, here also NH3, and here NH3, and one SO4 ligand, that is OSO3. This is the structure of the coordination compound. We will take another coordination compound, that is CONH3 4 times SO4. Okay, positive charge here. Okay, if you write the structure of this coordination compound, what will be the structure? Here CO, which is attached to 4 NH3 ligands, here NH3, and here oxygen single bond sulfur, here oxygen single bond, here double bond O and here double bond O. In this case, this is the structure. Okay, in both the case, there is SO4 ligand, but in this case, it is acting as monodentate ligand, and in this case, it is acting as bidentate ligand. Here, it is bidentate ligand, and here it is monodentate ligand. Okay, so these type of ligands are called as flexidentate ligands. Again, flexidentate ligands or polydentate ligands, which shows variable denticity according to the requirement of the metal. And you can also consider EDTA 4 minus and EDTA 3 minus. Okay, here 6 donor atoms will be there, and here 5 donor atoms will be there. Okay, so this is also an example for flexidentate ligand. Ligands are also classified based on the charge on it. Okay, charge on it. Okay, the first classification is cationic ligands. Cationic ligands. So the name itself says that the ligands which carry positive charge. The ligands which carry positive charge are called as cationic ligands. For example, okay, NO plus, which is called as nitrosonium, and NO2 plus, which is called as nitronium, anionic ligands. These are the ligands which carry negative charge, and here name of the anionic ligands should end with O. For example, consider Cl minus. Okay, it is an example for anionic ligand because it carry negative charge. You should not write it as chloride. Instead of that, you have to write it as chlorido. Okay, chlorido. Because while naming the anionic ligands, it should end with O. Okay, therefore it is chlorido. And one more example, Cn minus, it is not cyanide, it is named as cyanido. Okay, cyanido. Okay, next type of ligand is neutral ligands. So these are the ligands which do not carry any charge, Okay, for example, H2O, NH3, okay, and CO, NO. In majority cases, neutral ligands are named as same as the name of elements, but there are some exceptions. Okay, these are some exceptions. We will see how these neutral ligands are named. Okay, here H2O is named as aqua, and NH3 is named as amine. Okay, CO is named as carbonyl. NO is named as nitrosyl. Okay, these are exceptional neutral ligands which are named by using special names.
Thank you for watching.